something that I picked up from my team. So like they just mentioned, I'm from Canonical. I work with the public cloud team there. And all my different squads, they work with different public cloud partners. We all are into confidential computing big time right now. It's a hot topic. They are interested, we are interested, and the rest of the world is pretty much interested, especially if you want to ensure that your data remains secure. And you're worried about your sensitive data going on the cloud. So that's what we're going to talk about today. And let me just see if this works. Okay, that's the pointer. And how do we go ahead? Okay, cool. So, okay, and that's my shadow. Cool. The agenda, we'll look at what is confidential computing, why do you need it, and how is it implemented. That's the basic thing we'll look at. But it's also a very involved topic in the sense there are a lot of different security concepts involved. So to get a feel of what the whole thing is about, we are going to look at different threats and what we can do about those threats. So that's usually the security measure. It's usually some sort of a theoretical concept. And once you have that theoretical concept, how do you implement it? That is usually the enabling tech. So most of the concepts involved in confidential computing, that's the way we will cover it. So let's just go ahead and start. So the main problem is problem of trust. So that's what we're going to look at throughout the presentation. What do you trust? If you have a physical machine, say, it's got hardware and operating system and applications on top, can you really trust all of them? No. Sure, of course. Yes, you can't. Definitely. And we'll look at each of those. We'll try and see if we can trust anything at all. It's very difficult to trust anything, but we'll see if we can do that. And the bigger problem, once the machine goes out of your hand and you want to use the cloud, it goes into this cloud, then suddenly everything is out of your hand. The whole hardware is the cloud's hardware, and they control everything. So everything from the hardware, the OS, the hypervisor, they have access to the actual infrastructure, and your VM, your small little VM, is now underprivileged. All these other things are more privileged. So in this case, security becomes even more difficult because they can access everything that you put in there. So how do you believe them? Do you want to believe them? You don't want to believe them, and you want to see what you can do about that. So this is the problem we're going to solve. The problems of having a local, I'm sorry. Okay, let's. So problems of having a local machine, you solve that first, and that machine goes into a cloud, and pretty much everything remains the same. So you need to solve the problems of the local machine. Okay, so what are the things in a local machine? I'm hoping I will get used to this soon. Yeah. Okay, so first thing is the hardware. Now, unfortunately, there is something you have to trust. And the easiest thing to do is you trust the hardware, because it is at this level that if someone wants to really tamper with it, they have to go to a lot of effort. So you believe that the chip that is made, the chip manufacturer is true. He or she, the entity, wants their customers, they want things to work. So they will not tamper things, and they will keep it all safe. So we are going to take hardware as the point where we trust. Something needs to be trusted, so we trust the hardware. What about the firmware? Firmware is what runs the hardware initially. So that can be tested. I mean, so the hardware, when it comes up, it can just verify the firmware and ensure that it's the correct one, and we can trust the firmware. Next thing is the OS. Now, OS is something that we really need to take care of. There are a lot of things that can go wrong there. We'll look at some of those, so there's a lot of effort there. And finally, the apps. You definitely can't trust apps, but that's your job. You're creating the apps, so you better try and make it as safe as possible. So that's outside the domain of confidential computing. So we are mainly going to try and stick to confidential computing. So let's look at the operating system. So first thing, you boot up the system. Well, the boot process itself could have a lot of problems in there. So we'll look at that. And all of those concepts are very relevant to confidential computing, so we'll look at that initially. But there are also a few other things that you can do with the OS, which is required, which is very useful, which is required, but not directly relevant to confidential computing. So we'll just quickly look at some of those things and then go ahead from there. So the first thing is you harden your system. That means make all your configurations in the system secure. So do things like remove all unnecessary components, software packages, disable all the unused hardware ports, you configure very strict file permissions, secure the network services, and so on. Or configure remote logging so that you have your logs somewhere outside, and if a hacker comes in, hacks your data, they can't delete their logs because your logs are somewhere else. So you need to think of a lot of such things, and these are like hundreds of things to do. But then there are various ways to do this. Ubuntu has got this Ubuntu security guide, which ensures many of these policies. There are standards available, benchmarks used in the industry. So that USG, the security guide, basically uses those benchmarks to help you do all of this automatically, to create scripts for you, to create remediation scripts and compliance related trails. So that's how you secure your OS. Another thing that you can do is secure your application. You want to basically say that this application does this, which for this particular thing to do, it needs a few accesses. Let's say it needs to access the file, it needs to access one particular service, and so on. So you limit its access to that and only that, so that if it gets hacked, it can't access other services. So that's basically access control. And it's called the principle of least privilege. So again, there are ways to, there is something called as App Armor. I think there's a session later on in this session, either today or tomorrow. So that's again a Linux security module which helps you do this easily. So it has some security profile for each application, and and it's already pre-installed for most applications. If it is not, you have the means to actually generate a security profile. It's pretty easy. You just put it into complaint mode and run the application, make it do everything that it can do, and it records all of that. So then that becomes the basis for running it later. So anything it tries to do beyond that, that's not allowed. And finally, there's this this is like the most obvious thing to do. You want to handle vulnerabilities. You're dealing with software, so obviously there are going to be bugs, there'll be hackers, malwares, all sorts of things. But the safest thing and the most basic thing you would do is ensure that keep your software up to date. You keep getting all the patches, and you keep doing that regularly. And in fact, you might even do it, if it is my team, we actually do it every day. So because we generate new images every day with patches every day. So this is something you can do. Again, there's help available. Ubuntu Pro is available, which lets you do this, and it's also backports stuff. So anyway, so there are many ways you can do this. So that's the OS, the high level. Now, what about the actual boot process? The main thing that we are initially looking at. Can we trust the boot process? Yeah, that's actually the answer to everything. And in the end, you'll have to answer why, if you can't trust something, what can you do about it? We'll look at that. And then if you can answer that, that'll be the real answer. So, yeah. So what's the boot process? Well, it's the firmware that initially comes up, the first thing that runs. It does some initial hardware checks, then it looks for the bootloader. The bootloader finds the kernel, and then the kernel finally loads up all the drivers and the root file system. So that's your standard boot process. And you want to check how to trust this. Can we trust it? So have the modules, any of those modules been tampered with? And are they all the correct versions? So these are the questions we need to answer. You wouldn't think of, boot process, but no, there are rootkits, bootkits. People have physical access to it, and they can actually play around with the boot process. So how do you solve that? The solution is called secure boot. This is one of the security measures. And what it does is mainly it ensures that all of these modules are trusted. And also you verify that it is trusted, that it is being created by some authorized vendor. So that's the basic idea, that it only allows trusted modules to be loaded, and to ensure this process continues, each module verifies the authenticity of the next module. So a chain of trust is created, and if any one of those fail, then the boot process is stopped immediately. So that's the basic idea of secure boot. So what is trusted module, and how do you actually verify it? Sorry, any questions? Okay. So trusted modules. One thing is it could be from a authorized vendor. So if you are using Ubuntu, you'll have Canonical signing those modules, and so you believe that, okay, these modules are signed by someone who's authorized, who's trusted. I trust that person, and which is why I'm okay to use that module. The other option is, oh, maybe I'm developing those modules. You want to do some debugging, and you want to try some stuff out. So in which case you're not going to sign, or you might not have a key, or you don't want to sign it every time you want to create a new version. So you want your modules to go through the secure boot process and work, but at the same time you don't really want to sign it. So you want to cater to these. So these are basically what trusted modules are. And now you want to verify them. So what do you mean by verifying? Well, first thing you want to do is verify the vendor. And once you know that it's from the correct vendor, you want to verify that whatever the vendor said they are giving, that's exactly what you have. So that's where you're verifying the vendor. That's the first option. And the second one is where you're verifying the module content itself. So if you are developing the module yourself, then what you have developed, that is exactly what is there. Someone hasn't changed it. So that's the verification that needs to be done. So now, so we're going to, there's a lot of, so there's a lot of cryptography involved. So a quick recap for those of you, I'm sure most of you have come across this at many points in life at some point, but we don't sometimes really realize what exactly happens. So a very quick recap of what asymmetric cryptography is. That's what is being used here. So first of all, it's just a mathematically linked pair of keys, one public key, one private key. The public key is shared with everyone. The private key is yours. It is confidential. It's not shared. One of the main uses is to encrypt, which gives you confidentiality. So the person sending the data will encrypt it with their private key, and at the other end, the receiving person will decrypt it with their public key. Now, and this, wow, I said it exactly the other way around. Well, it happens. So the next thing what I just said will come in the next slide, which is about checking about authenticity. Sorry about that. But here, so here you encrypt with your public key. Anyone who wants to send, so you all want to send something to me secretly, you use my public key to encrypt it and send it to me, and only I can then decrypt it because I have the private key, and that's needed to decrypt it. It's very difficult to find that private key and so on. The second thing is about authenticity and integrity. So this is where digital signatures are used. They achieve this, and we'll see how that is done. So the signing authority, so let's say Canonical or whoever is signing the module, what do? Whatever is the data, so they generate a hash out of it. This hash is very specific to that data. Even if a bit is changed, the hash will change. So keep that in mind. And then they encrypt it with their private key. So that puts in a signature, a digital signature to it. And that data as it is sent across to someone someone has it, who is verifying it, and they also get that digital signature here. So they do two things. One is, first of all, they decrypt it using the public key, and that proves that it was sent by that person. So since the decryption happened, so it's authenticity. And they also do this, they just generate the hash on their own, and then they verify whether these two hashes. So when you decrypt, you get an original hash, and when you do a new hash, you get the new hash. So you just check the two of them, and see if they are the same. It basically means you're good. The content is what it was supposed to be. Okay. Now coming back to our actual problem, secure boot. We want to just check how this verification actually happens. So these two are, let's say, signed by Canonical, and we want to verify them. So what happens, Canonical or whoever the vendor is, they will take the compile grub, the binary, I'm just taking that as an example here, generate the hash, sign it with their private key, and attach it to that same executable file. So this is what comes at the, that is what you will see in your hard disk when you are trying to trying to load the grub. And so how do you verify it? So you need to separate those two things. The hash part you decrypt using the vendor's public key, which you will need to have, and the actual data you just generate your hash on your own, and then again check whether the two of them are same. So when you do that checking, you know, oh, okay, it's the correct one, it's come from the correct person, and it's what is expected. Now the other case where you created the module. In that case, what's your process? Well, you just generate the hash and store it, and you need to know that, and whoever is verifying it will also generate the hash, and then we'll just check if it's the same. So in this case, what they need to know is basically the trusted hash. So there were two things that if you want to verify, two things you need to know, either the public key of the authorized vendor or the actual hash. So how do we get that? It needs to be there somewhere, and that is where UEFI comes into picture. That is the enabling technology for all of this secure boot that I've just been describing. So UEFI is, well, it stands for Unified Extensible Firmware Interface. It is the newer version of BIOS. It's what runs the first when you boot up all your modern machines. It defines your firmware architecture basically. It's a spec which defines the firmware architecture, and it also defines secure boot. Now, those two things that we need, where are they? They are stored in the UEFI's non-volatile RAM. So there is this thing called as a signature database, in which it stores the digital certificates of trusted vendors, and it also stores the hashes of trusted modules. So these are the two things that you want, and this basically is this database which contains a list of all the allowed people, allowed vendors and allowed hashes. Okay. Now a question, is that enough? Just having an allowed list, is that enough? Same answer. No, most answers are no. So yeah, so it's not enough. What if the private key gets stolen? What happens in that case? Well, you have your public key there, it's in the allowed list, but the private key is now stolen, so you don't really believe that vendor anymore. You need the new public key from that vendor. What if those trusted modules in there have vulnerabilities? They were detected later, and but we have already put the hash in there. So then what? So we have an additional thing for that called the revoked signature database, in which you will put in a banned list. So everything that shouldn't be there goes into this list. So revoked digital certificates, hashes of known malware, so things that you're sure are bad and you want to ensure they shouldn't come in. So you create hashes of those. They could be signed or unsigned. And finally, you also put in signatures of those vulnerable modules. Now all of this becomes the banned list. And what actually happens? Well, the UEFI, it will load a module only if it is in the DBX or not in the DBX. Not in the DBX, that's this. It should not be here and it should be here. If that's the case, it will load the module and it'll go ahead. If that does not match, this boot process will stop. Now, the modules are all trusted, but are they the specific expected ones? So let's say you're trying to use your laptop and join to a secure network. and your secure network wants to ensure that your laptop is safe. So they have a specific set of modules that these are the versions of the different modules that are allowed. So they create a policy for that and they say, oh, only this, if it is there, only then we are letting you in. We don't care if what modules you have are trusted or not, but these are the versions that we want. So if you want something like that, or also if there is some other new unknown threat which manages to get a signature from a authorized entity, that could come in. So we want to solve this problem. How do we do that? Another thing called measured boot. This is the next security concept. Now measured boot is also part of that same UEFI specification. What happens is your secure boot functions as it is, but while you are loading each module, you also measure it. By measuring it, you basically mean you take a hash and then you store it in something called as a TPM. We'll see what that is. That's the enabling tech. So you store it there, and that creates a verifiable audit trail. So if someone wants to, so that secure network server wants to ask, it can ask, oh, tell me what modules you have inside, and that will give you these measurements. And are you giving me the correct measurements? Well, the TPM says I have signed it, and TPM is again this secure thing, hardware thing, which we are going to believe. So you get this report. It's called as an attestation report, and that allows the remote server to give you access. So this whole process where the remote server asks for some proof is called remote attestation, and it verifies. So the remote server will then verify the log, and it will grant access only if that machine fits within the stated policy. Okay, now the TPM that we were talking about, that's a specialized tamper-resistant security chip. It stores sensitive data like encryption keys and passwords and so on, and it does all encryption-related functionality outside the CPU. So it's a very safe little chip which does everything related to security, and you can believe in it if you believe the chip manufacturer. And it's all in hardware, in logic gates, so no one really can play around with it unless they are in some way attacking the chip manufacturer itself. Okay, so the hash values themselves are stored in something called as the platform configuration registers of the TPM, and these registers are what is signed to create that attestation report, the audit trail log. Okay, ready for the next question? Everything is trusted till now. We have the whole boot process, the modules, they are all trusted. And now we go ahead and we want to just launch the root file system. Is that trusted? No. Because if you have physical access, you can modify the boot modules. Of course, you can just pick up the hard disk and open it, put it into some other machine and see what's in there. So that's like a very basic level of security threat. And well, there's a very simple solution which I'm hoping most of you use or should use. If you don't, it's called full disk encryption. So the idea here is that you encrypt everything on the hard disk, and every time the CPU needs to access data, it will just encrypt, it will just decrypt the data and use it, and then you want to store it back, it will encrypt it and store it back. Now, so there is, the way this is done fast is basically using symmetric key instead of asymmetric keys. They are much faster, and you also have a hardware accelerator along with the CPU, which makes these things very fast. So your normal operations, you don't realize that your hard disk is encrypted and everything works as usual. Now the key itself is stored on the disk. Does that make sense? No? Yes? Someone steals the hard disk, oh, the key is there, right there, open it up using the key. No, so what it is on the disk, it needs to be on the disk, but it is encrypted and sealed using another key. So what is this other key? It's basically the password that you enter when your machine boots up. If it's a user-based, password-based, passphrase-based system, then it's this password. So a key based on that password, which encrypts the main key. And if you happen to have a TPM also, then we can use the TPM to do that. You don't need your password or passphrase. The TPM will create this other key, and it will do the encryption. and the hardware accelerator, like I said, makes the whole thing very fast. Now, if you have that TPM, there's an additional protection that you can get. What is that? So, okay. So the TPM, it will unseal that key only if the machine state matches expected policy. Now the TPM, we already know it's got all these policies inside there saying what is the state of each module. It's stored there. So you can do something called as local attestation. That's here. So when the kernel wants to load the root file system, it has got two options depending on whether the TPM is there or not, whether it's a user-based password or it's a TPM-based thing. So if it's a user-based password, it will just ask the password for the user and then get the key unsealed. And if it's TPM-based, then you ask the TPM to give it, but the TPM won't give it unless the rest of the modules are all secure, are all matching that policy that has been decided. So that is called as, this is called as local attestation. The TPM itself does the attestation. Now, next question. We are done with the local machine. We have tried it as much as possible. We have tried to make it as safe as possible. And now we move that small little local machine into the cloud. It goes into this cloud where everyone else can access it, including other VMs. So can we trust anything? Now that's the question. Answer this time? No. So what do we do? This is the answer I want. What do?
We don't put sensitive data in the cloud.
You don't put sensitive data in the cloud. Yes, but no. Okay, no. Yeah, we can think of many reasons why no. Well, people want to use the cloud infrastructure. It's huge. It's easy. There's a lot of which you can't really have on a small machine if you're running maybe machine learning and lots of other things. So if you need to use the cloud infrastructure, what could you do?
Homomorphic encryption.
Oh yes, homomorphic encryption. That is one of the initial solutions that were proposed, but it is pretty difficult and has not yet been really implemented. So which is why we had to come up with other ways of, but cool, very nice. Anything else that you can think of? Decentralized network. Who said that? Whoever, yeah, but how does that help? Sorry?
Like a photon is built on decentralized network.
Okay, I can't really hear you, but assuming we are talking about general clouds, you want to use the public clouds and their infrastructure, just having a decentralized network, I'm not sure what you mean. Maybe you're thinking of a private network of your own, or I'm not sure what, but maybe we can talk about that. Come to me later and then I'll try to understand what you're trying to say. I didn't really intend this to be a question answer thing, sorry, but I'm just so used to doing that can't help it. Anyways, so now the answer here is that we cannot trust anything in the cloud, so we change the problem itself. Instead of making it a problem about trust, we decide that no, we can't trust anyone. We will assume that our data is going to be accessible to people. So in that case, what do? We try and protect the data. So now the problem changes into protecting the data instead of trying to trust someone. So what? So there's data at rest, which is on your hard disk or on the hard disks of the cloud. There's data in transit, where the data moves from one place to the other. And finally, there's data in use. That's when the data goes into the CPU, into the RAM, and it's actually being used. How do we secure it? These two, the first two, at rest and in transit is pretty simple. We've got it down pat. Encryption. So you use full disk encryption for your disks, or anywhere, everywhere you use TLS. You use encryption to ensure that these things are protected. But data in use is the part that's still, well, we can't say that still because I'm talking about it, I'm going to give you a solution, but has been till very recently not very safe. And if you don't use confidential computing, it will remain unsafe. So you better start using confidential computing. Anyways, so what is data in use? This is when your data actually comes into the RAM and the CPU is playing around with it. at that point of time, you still want it to be safe. And remember, you're in the cloud environment, the host OS, the hypervisor, all of them have access to your RAM, and they can give instructions to the CPU. So they have access to everything, and you still want to make it protected. So what do? The solution is confidential computing. What is it? You create something called as a trusted execution environment. So you ensure that your RAM itself is encrypted. So even if the host or the more higher privileged entities try to access it, all they can see is garbage. And how does that happen? Well, the CPU has got this special memory encryption engine inside, which for every memory access will access this RAM, get the encrypted data, decrypt it inside the CPU, then work on it, and when it wants to store it back into the RAM, it will again encrypt it. So the only place where your data is now clear text is inside the CPU. And like I said before, CPU, small chip, hardware, we believe the CPU. So that's the only thing we believe in, that's the only thing we trust. So there are three main things that we are trying to achieve here. First one is isolation. So isolation meaning only your VM should be able to access your specific RAM pages, no one else. Not the hypervisor, not the host OS, none of the other VMs, no one else. Only your own VM will use it. Second thing is, if the time up? Oh wow, sorry. Okay, let me just quickly finish. Yeah, we are done. This is the main thing and the last thing, so we're almost done. Okay, so yeah, so the data is encrypted, and attestation, you need to, so just because the cloud provider says that, oh, this is all, this environment has been set up, doesn't mean we can believe them. So we need some sort of proof that it is actually set up. So how is it actually implemented? So this is, okay, so first thing is, so the security coprocessor, that is what is one of the main things. It is something like a TPM, very secure, but that helps you decide. So there's a given VM. So I'm just going to take like 5 minutes more. Bear with me. It'll be done in like 5 minutes. But this is the important part. You need to understand this to understand confidential computing. So you create a VM. How do you ensure that only this VM gets access to its pages? So a unique ID is created for that VM. This processor creates that unique ID, and for that VM's pages, memory pages, it assigns that same unique ID as the ownership bit of that page. And here there's this memory management unit which uses those bits to decide whether to give access or not. So whenever some code is running, you know that this is the code running because that particular unique ID is in the current context. And the memory management unit also knows, oh, which page we are going to try and access, and it knows the ownership bit of that page. So these two bits are compared, and only if they are the same, it lets you go ahead. So, so you get the isolation. These first two entities help you create isolation. Encryption is done by the MME, and finally, there's attestation needed. Attestation is again done both by the CPU, this coprocessor, and by a VTPM. Now, if VTPM is a virtualized version of TPM, it does everything exactly like the TPM that we talked about, but it's just in software. So it will create its own log. This one will create a log about this whole secure environment. It will sign it, the whole thing, and that will create the attestation report. Now, the enabling techs here are Intel TDX and AMD, and even NVIDIA now has that. And the last thing, how do we, when you launch a process, launch a CVM, what exactly happens using all of this? So the first thing is you create, ooh, what was that? Ooh, that is sad. Okay, okay. The hypervisor asks you to create a CVM, asks the CPU to create a CVM. The security processor allocates a unique ID, then it generates a unique memory encryption key for that. This key remains in that processor, does not go out anywhere. Then memory is allocated for that CVM. this same ID is set as the ownership bit for that memory page. The encrypted pages are then, the pages are then encrypted with that key. The CVM is then loaded with the UEFI firmware, the actual machine that you want to load. The processor will create a hash of that firmware because it needs to store it in the TPM. And finally, it'll say initiate a virtual core and launch the CVM, in which case the CPU will transition to this guest secure mode. It will activate that ID. So now the current context is that unique ID for that VM. It will begin executing the firmware, and the VTPM is initialized. So you store the hash in the VTPM and you finally continue with the boot process, and everything continues as before. So in effect, now we have seen this multiple times. We know now it's all secure internally and externally. And these are the different things we have looked at. It's just a summary of what we just looked at, the different threats, the security measures for each of those threats, and what the enabling technologies are. So this was about the boot process, this is about confidential computing, and the middle thing is about the OS. And that's it. You can find all of this in all major public clouds, and these are the companies that enable it. Thank you. Yeah. I didn't miss. Okay, so it depends actually a lot on what sort of thing you're running. So for many standard things, you won't see any impact. It is pretty fast because there's a hardware accelerator inside. But for things like machine learning, where a lot of data is being processed and a lot of pages are being swapped from RAM all the time, then you will see some impact. So there it will slow down a bit. But if it is where not a lot of memory is being used all the time, then it is pretty much like your FD thing.
Do you recommend for the data science purpose?
Yes, it is in fact used a lot for data science, because different companies, let's say they all want to work on some confidential data, and you want a lot of data, so you can't share data between companies. But using this, you can actually work on all of those data, and none of the companies see each other's data. So yes, definitely you can use it for data science. In terms of performance, it will affect your performance, but that's something happening on the cloud, so wait for a bit.
So basically build on mass.
Mass, someone from Canonical in mass will answer that question. Yeah, sorry, I'm in a hurry, yeah.
The setup for this is enterprise level, or everyone can do it? Are there documentations to achieve this level?
Oh, all of those clouds have extensive documentation about this. It is a it's very easy. You can, whether enterprise or your own, you just have to pay the money to launch that particular instance. And while launching the instance, you can just select confidential computing. It's called trusted launch. You just tick, you can say, I want secure boot, I don't want secure boot, I want FD, full disk encryption, whatever. Yeah.
The security model for this does need to trust the cloud provider, right?
No, you don't need to trust the cloud provider. That's what I've been trying to tell you the whole 1 hour.
Yeah, but the keys for the trusted RAM need to be stored somewhere, right?
The keys for the trusted RAM are stored in that security coprocessor, and that is a chip. It's all in hardware, it's in logic, and that key never leaves that chip.
I see. So the security model does cover that being malicious as well.
Sorry?
The model does cover the cloud provider being malicious as well.
Yes. The model definitely. So everyone, if you got nothing out of it, take this out of it. You don't have to trust the cloud provider, and that is the basic idea of confidential computing. Okay. Anything else? Thank you.